Hello friends, it's David, aka Delta G, and welcome to my channel. In this video, I'm going to show you how I set up the capacitive touch unit on Arduino's new UNO-R4 boards. The UNO-R4 replaces the old ATmega 328P chip with a new Renaissance chip, the RA4M1. In addition to a lot more speed and memory, this new chip brings a lot of new features and peripherals to play with. One of those is the Capacitive Touch Sensing Unit, the CTSU. In a previous video, I showed you a library called LoveButton that uses the CTSU to turn the love pin on the back of the R4 into a built-in touch sensor. In this video, I'm going to show you how I made that work. Now, the unfortunate thing about the CTSU is that nothing is included in the core other than the register definitions, and it isn't in the part of the FSP that we get. So we'll have to go bare metal and deal directly with the registers for this one. There's a lot of ground to cover, so it's going to be a long video. Let's start by looking at how the CTSU works. I'll be looking at the RA4M1 Hardware User's Manual. I'll put a link in the description. We're going to start in section 41. Capacitive touch sensing works by measuring the stray capacitance on a small metal touch electrode against all of the different things around it that can provide a ground, like other components of the circuit board, any type of enclosure it's in, even the earth itself. When you bring your finger in close to the electrode, an additional capacitance builds up between that electrode and your finger, and that adds to all of this other capacitance. And it's this change in capacitance that we'll be looking for when we do touch sensing. The capacitive touch unit in the RA4M1 has two different modes. It has a self-capacitance mode where it does just what I described a moment ago, and it simply measures the capacitance at a single pin. It also has a mutual capacitance method where it measures the capacitance on a receiver pin while it's also keeping a nearby pad either high or low by transmission. What it does is it measures twice on the receiver, once with the transmitter high and once with the transmitter low, and then it looks at the difference between those two capacitance measurements. And this gives you a much more sensitive touch sensing, and it also gives you a little bit of the ability to make these sort of matrices. Now, I don't know a whole lot about the mutual capacitance method, so I'm just going to stick to self-capacitance for now. The other thing that the capacitive touch unit can do is it can set up for multiple pads. So you can either do a single scan or you can do a multi-scan. For the purposes of this video, we're just going to stick to a single pad. Figure 41.4 shows us the measurement circuit for the capacitive touch unit. Here we see our capacitive touch pin that we're going to connect to our electrode, and it's connected to a pair of switches. These switches will charge and discharge the capacitance on this electrode. And what the capacitive touch unit is actually going to do is measure the charging current going into this electrode. There's going to be a sensor drive pulse, high, low, high, low. When it's high, it will close the top switch, and when it's low, it'll close the bottom switch, and that controls the charging and discharging. When the sensor drive pulse is high, switch 1 is closed and the current flows into the sensor electrode. This current is measured by a special type of clock called a current controlled oscillator, ICO. This clock varies its speed based on the amount of current that's flowing through it. So more current means a faster clock. So when we bring our finger in, we have more capacitance, that creates more current, that creates a faster clock, that creates a higher count on the counter. When we have less capacitance with no finger, we have a lower current, so we have a lower count. Because this count is going to be affected by all kinds of different things that could happen in our circuit, like supply voltage fluctuations, there's a second current control oscillator called a reference clock that's also running off of a reference potential. And what we'll actually do is we'll look at the difference between those two counters in order to tell when we have a touch. Additionally, because this current is pulsing in and out with this sensor drive pulse, we've got this TS cap pin here, and we're going to hang a capacitor off of that. This is a piece of hardware we're going to have to add. It's going to act as a low-pass filter to sort of smooth out this current so the ICO can make a continuous measurement. When we make a measurement with the capacitive touch unit, it's going to take several of these drive pulses and sort of add them together at once. We'll actually get to set that in one of the registers. We'll set how many drive pulses we want and then how many times we want to repeat that. But say we take 3 drive pulses. It'll close this switch 3 times, and this current is flowing that whole time, and this ICO is going to measure that current. So that's how it works. So let's look at what we got to do for the code. So if we go to figure 41.9, it gives us a basic flow chart, step by step, of what we have to do to power on the unit. We start by discharging the capacitor, we set up some pins, and then we just start enabling things and powering them on. We'll go through these steps a little more in detail as we write the code. If we go to figure 41.12, this gives us a little more holistic view of the whole measurement cycle. We start at the top with initial settings, and that's what we just saw. And then there's a whole bunch of other settings to make and decisions to make, and we'll go through those kind of step by step as we write the code. Then we start the CTSU. So there are 3 interrupts that we can hang off of here. The first is a write request interrupt, CTSU WR, and this happens right when it's ready to start. It needs to know what pin to use, and it needs to know what settings to use. Generally, the CTSU is meant to be used with the direct transfer controller, and I don't quite have code ready for the DTC. So we're just going to hang regular interrupts off of these. Normally what would happen is, instead of being hooked to an interrupt, this interrupt signal would trigger the DTC to simply transfer that data into the registers where it needs to be, and then it would go to the next step. We're going to have to stop here with an interrupt and actually write those registers, because like I said, I don't quite have code ready for the DTC. So once everything's written in the registers, it moves on to the next step and does the measurement. At the end of the measurement, it gives you the CTSU RD interrupt. This interrupt tells you that you're ready to read your results out. Again, what's intended to happen is for this to fire off the DTC to transfer the results directly into memory wherever you want to read them from. We're again going to hang an interrupt off of this and simply read them right out of the register. If there's more pins to be read, it'll go back and give you another WR request, and you can, in multi-pin mode, you can go back and read more pins. When you get to the last pin and there's no more pins to be read, it gives you the CTSUFN interrupt, which is an end function. And again, this is really only useful if you're using the DTC. Since we're firing an interrupt up here at RD, we're going to know when our measurement is over with. If you're working with multiple pins in the DTC, though, you may have this cycle going through multiple times, and then this FN interrupt fires at the very end when everything's ready to go and read, and it's sitting in memory where you want. The one other thing we got to look at, and this was what really jammed me up when I got started with this, is this status counter. So there are a lot of different steps to this process of making a reading, and there are places in this process where we have to stop and either write registers or read registers. And because of that, there's a status counter that keeps track of what step you're at in the process. So there are certain places along this pathway where you have to jump through certain hoops in order to get to the next step. And that was what jammed me up, because there are certain places where you have to write to a register even though you're not going to change it. That's what triggers you to go to the next step. So basically it starts off in status 0, and that's a stop state. It's no trigger and nothing's happening. Once we give it a trigger signal, and we can either do that with an event link or with a software trigger. We're going to use a software trigger today. Once we give it the start signal, it moves to status 1. And so this is our measurement channel updates. We have to get the channel ready. In order to go into status 2, we have to update the measurement channel. Even though we're only using one channel, we have to write to that register or it won't move us to status 2. In order to go into status 3, which is where we're waiting for our sensor drive to stabilize, in order to go to status 3, we have to write to the CTSU SO1 register. So what they did, since again this is meant to be used with the DTC and they don't know how many registers you're going to change or how much data you're going to move, and they didn't want to try to hang this off of another interrupt signal, what they did was they made it so that this CTSU SO1 register triggers the transition to the next state. So if you've got a lot of things to do, or if you've got a few things to do, whatever you've got to do, just make sure that writing to that register is the very last thing, and then that triggers you to go on into status 3. So again, even though we're not going to change the value in this register, we have to write to it every single time we get a WR interrupt so that we can move on into the next status. So once we're in status 3, we're going to go down to status 4. That's our measurement start and our measurement period. In order to get into status 4, we got to have a flag that goes. That all happens automatically. Once the measurement is over, it goes down to status 5. The measurement is completed. It gives us the RD interrupt. We go and read our registers, and then it cycles back up here and sees if there's more pins to read, it'll go back to status 1 and keep flowing through this. Since we're only using one pin today, it's just going to end right there, and then we'll fire another start condition to get from status 0 back into status 1. So I took all the information from those flow charts and built a empty Arduino sketch basically as a comment skeleton. So what I did was I started an empty sketch and I just created functions and filled them in with comments, step 1, step 2, step 3, everything we've got to do going down. I made an initial CTSU setup function. It's got all the stuff from figure 41.9 and figure 41.12, all the registers we need to set up. At the end, you've got step 9 to enable the interrupts, and then step 10 will start a measurement. I also filled in 2 functions for the interrupt handlers, a CTSU WR handler and a CTSU RD handler. So for the write request handler, that's going to be when we're at status counter 1. In order to get to status 2, we have to update the measurement channel. And in order to get to status 3, we have to write to the CTSU SO1 register. So if we'd had anything else to do in there, we'd make sure we did this step at the very end, because that's going to kick us into status 3. For the RD handler, that's at status 5 when we're all the way done and ready to read. So the first thing we're going to do is read the results from the counter registers, and then we're just going to start another measurement right there. And then since there's 2 places in the code where we have to start a measurement, and I don't like to repeat myself, I made a start CTSU measure function so that we can use it to start our measurements. And I just made a couple of notes here. There has to be at least one measurement channel for the software to start. So what will happen if you send a start signal and you haven't enabled any pins and haven't designated any pins as your measurement pin, then it simply bails back out of status 1 and goes right back to status 0. It'll never actually start the unit. So even though we're not changing our pin number, in every cycle of this, there's 2 places we have to go write that register again just to make sure that it'll go to the next step. And like I said, this will be a lot easier with DTC, but that code's just not ready yet. And then in that start CTSU measure, we're also going to start there's a bit we're going to hit in the control register 0 that will do a software start for our measurement. So now let's talk about the pins we're going to need. I'm going to use an R4 minima for this. You can also use the R4 Wi-Fi, but the pins are going to be a little bit different. I'll try to point out where the differences pop up. I'm also going to use, just because it's there and it's easy to use, I'm going to use the love pin on the back of the board, the little heart-shaped blob of solder. That way I don't have to try to hook up anything to a pin. It's just already there. It's a nice little pad, and it's going to be easy to use. If we look in the schematics, the love pin is pin 204. That's port 2, pin 4. And if we go into section 1.7 in the hardware manual and look up pin 204, we can see that it is TS00 on the CTSU. So it's touch pin 0. We can see we also going to need the TS cap pin, and we can see it's up here at 205, and we don't have 205 broken out on the board. But if we go look at pin 112, TS cap is also there on pin 112. And 112 on a minima is digital pin 10, and on a Wi-Fi it's digital pin 7. So we're going to use that pin for our TS cap pin. You can also see here pin 113, that's the love pin on a Wi-Fi, and you can see that it's touch pin 27. So if you're going to use a Wi-Fi, you're going to use where we go to touch pin 0, you're going to go to touch pin 27. Okay, so let's get started filling in the code. The first 2 steps are all about the pins. Step 1 is to set TS cap as output and low and discharge the capacitor. Now we could just use pin mode and digital write to do that, but we'd have to use pin 10 for a minima and pin 7 for a Wi-Fi. Since it's the same pin at the chip and we're doing everything else bare metal and we can do it all in one line, we're just going to go straight for the pin function register and do a direct write there. Step 2 is going to be to set up the PMN PFR register as peripherals, so to set our pins up as their peripheral functions. So we're going to start over here in 19.2.5, the port MN pin function select register. Section 19 could be a video all on its own. I'm only going to focus on the bits that we need for this project right here. For the first step, we're going to need the PDR bit. That's the only one we need. If we make the whole thing zeros and only set PDR to 1, that makes us an output and a low level, and that's what we've got to be. So that's going to be our first step. That's going to discharge our capacitor. I'm not real sure how long we've got to wait there, so I just put a delay 1000. That's way overkill, and we can come back and calculate that later maybe. So the next step is to set up our pins as peripherals. So that's down here on the next page. We're going to need the PMR bit. That turns a pin into a peripheral function. And then we need the PCell bits, the PSEL bits. There's 5 of those, and that selects which peripheral you want the pin to be acting on. So we go down here to 19.6 and scroll down to pin 113. And we can see that to turn it into, or pin 112, I'm sorry, and to turn it into TS cap, we need 01100. That's OC. So we're going to go over here and put in that line. It's really long. So again, all we're doing is taking port 1, pin 12, and we're running a 1 in to PMR and OC into PCell, and everything else is going to be 0. We're using equal. So now we got to do the same thing with the sensor pin, and the sensor pin is the love pin on 204, and it's going to be the exact same bits. It turns out that it's OC for anything you want to put on the CTSU. And so that takes care of step 1 and 2. We've got our pins set up. The next thing to do is to enable the CTSU in the master stop register. So if you haven't dealt with any peripherals on the R4, in section 10, there is a master stop register that there's actually 4 of them, A, B, C, and D. And these are for low power modes. Everything starts off with a 1, and that's turned off. You've got to put a 0 in there if you want to turn anything on. And so MST PC3 is the bit we want. We've got to turn that to a 0. So we're going to go over here, and we're going to use and equal not because we don't want to touch the rest of the register. We just want to make a 0 in that 1 bit. So we're going to use and equal not and then a 1 run into MSTPC3. In step 4, we finally get to the actual CTSU registers. We're going to start off with CTSU CR1. It's 41.2.2. So we're going to use this for the first for the first few steps. We're going to set the CTSU power supply. We're going to set the base clock. We're going to power on the CTSU. And then down here in step 8, we also have to select the operating clock. So we're going to look at all of these bits. So the first 2 bits are about the power supply, and we have to set both of those at the same time in order to turn the supply on. We're going to leave those 0 in this first step. Attune 0 is about operating modes and operating voltages. We're above 2.4 volts. Let's just stick with normal. Attune 1 is a power supply capacity. Again, let's just stick with normal. For the operating clock, let's just go with peripheral clock B. That looks fine to me. Again, 0s. And for the measurement mode, we're using self-capacitance single scan, and that's 0s. So it looks like we need all 0s in this register. So the next step, we're going to set the CTSU base clock. That's CTSU CR1 and CTSU SO1. We've already figured out that CR1 needs to be 0s. SO1's down here in 41.2.21. And there's a few things to maybe tweak on with SO1. We have some bits down here to adjust the reference ICO current, and maybe we'd want to tweak with that later, but let's stick with 0s for right now. And then we have a base clock setting. Wasn't really sure what to pick out of here, so I just went with the middle OXOF. That's going to be operating clock divided by 32. And then down here at the bottom, we've got a gain adjustment, and I'm just going to leave these at 0. there's no reason to mess with that until we need to. So that gives us a value to go in that register of OXOFOO. Right, we're going to put an OF right here. So we're just going to run that in there like that. Next step is to power on the CTSU. That's those first 2 bits in register CR1 at the same time. So we've already seen that. Let's pop that in there. We're just going to do a OX03, and we're going to OR equal it in there because we don't know what. Well, we've actually got zeros for right now, but we might set something different up here in the top. Next step says wait for stabilization. It doesn't say anything about how long or anything else. It just says wait for stabilization. So for right now, I'm just going to throw a delay 1000 in there. We're just writing test code. It's okay that we block for a second here while we set up. Step 8 brings us to that second flow chart from figure 4112. There were a bunch of other registers that it wanted us to set up there. The first one was to select the operating clock in control register 1, and we've already seen we need that to be 0. So let's look at this CTSU SDPRS register, the noise filters. That's in 41.2.3. So I don't have any idea what to do for these settings, but fortunately it just tells us the recommended setting is 3 for these bits. Recommended setting is 2 for those bits, and I'm just going to start with the thing turned off for right now. So if we put those bits in, we get OX63. So let's do that. The next one we're going to set is the stabilization time. That's 4124. And again, I have no idea, but it says to set these bits to 16, and it says to always set these bits to 16. So we'll just go with a hard-coded 16. The next thing we have to do is enable our channel. So there's 4 of these enable control registers, and you have to enable any channel that you want to be able to use. And this is important if you're doing multi-pins. So we're going to need bit 1 in this control register 0 in this control register 0. The other one we have to go get is our measurement channel register. This is where we set which channel we're actually measuring. So it has to be enabled in the register we just hit, and then it also has to be selected as the particular one we want. And for this we want TS00, and that's going to be a 0. Now we have to go back to control register 0. We haven't seen it yet, and we're going to pick our control start signals. So let's just look real quick. There's only 4 bits here to play with. There's one here to initialize the control block, and that's really handy because it just puts a 0 in a bunch of registers that you'd have to 0 out during some interrupt somewhere. We have a bit here to set some power saving enables. We're going to leave that at a 0. We have a bit here to choose which type of start trigger we want. We're going to go with a software trigger for right now. That's a 0. In LoveButton, I put it on an external trigger, and I triggered it off of an event link, and I'll talk about that later. And then we have a start bit, and this is our software start. We just write a 1 to this bit, and that starts our measurement. So to start a measurement, we're going to write to CTSU control register 0. We're just going to write a 1 to it, and that should start the unit. So for right now, we're just going to leave all that at 0s, and we'll come back and write a 1 when we're ready to start. The one other register that I saw was this DCLCK register, and that's down here in 41217. That's a high pass noise reduction, and it doesn't tell us that we have to do this, but I noticed that it has it says to always set these bits to 3 and these bits to 0. So I went ahead and put us a line in to set those bits there to 3, just because it says always to do that. So let's take a moment to look at some of the registers that we didn't set. So we're going to start in 41212. This is a transmit receive control register. If we were in mutual capacitance mode, this is, and there's 4 of these, and this is where we would set our transmit pin. We can go to 41218. This is our status register. This one's really important. It's got some flag bits in it for if we're in mutual capacitance mode, if we're on the first or second measurement, if the clocks overflow, when the data transfer happens. And it's also got that status counter that we talked about. So if we're not sure what status we're in, we can go back and check this. That'll come in handy if we start hacking with this thing. We have a noise reduction spectrum diffusion control register, and I have really no idea what to do with this, but it says if our base clock frequency is greater than 4 megahertz to set it to zeros. So I'm just leaving it with zeros. We have a sensor offset register 0, and this is just like CTSU SO1, except that we don't have to write this one every time. This sets the sensor offset adjustment. We're just leaving it at zeros. It also has a measurement count setting, and this is how many times we do the measurement or how many times we measure one pin in one measurement. So back here in the SDPRS, we set a 3 here for the number of pulses for one measurement, and then down here we're saying how many measurements to take each time, and we're leaving that at 0, so it's just going to be, it says it's that bits plus 1, so that's going to give us 1 measurement if we leave it at 0. 41222 are CTSU SC and CTSU RC. This is our sensor counter and our reference counter. This is where we're going to come get our data from in our interrupt. We also have an ERRS register that has for our errors, and it only has 1 bit, and that's if the TS cap voltage is in error. I haven't seen this go high yet, and there's not an interrupt you can hang on it, so I haven't really been checking it. That brings us down to step 9, attaching the interrupts, and this is where it's going to get tricky. So interrupts on the R4 are handled through an interrupt link controller, and that's a whole nother video in itself. The interrupt link controller is handled in the core through an IRQ manager class. Problem that we have is that the IRQ manager class doesn't have any code in it for attaching the CTSU interrupts. So we have to do this ourselves. Now, while it's tempting, we can go straight to the registers in the ILC and just attach our interrupt right there. That would work, but the IRQ manager also keeps a table of what interrupts it's using. And if something else comes along later and tries to attach an interrupt, it might try to attach that interrupt in the same slot that we used and just wipe out our interrupt. So I did what hackers do, and I found us a back door. I wrote a library about it. It's called Event Link Interrupt. And so we're going to have to go include that library. And basically what it's going to do is it tries to attach our handler to a very seldom used RTC overflow interrupt, and then goes in and searches the ILC table, finds that interrupt, and swaps out the code to make it point to our interrupt instead, whatever interrupt signal we want instead. In order to use it, we're going to need to keep up with what entry in IRQ Manager's table that we own. So we're going to need a couple of variables here to keep up with those 2 indexes. And then to use Event Link Interrupt, we need to know the event link codes for the events that we want to attach interrupts to. And we'll find that in table 13.4. And if we scroll down and look for the CTSU, we're going to have hex 4.2 for the WR interrupt and hex 4.3 for the RD interrupt, hex 4.4 for the FN interrupt. So let's throw those in comments. And then in order to use event link interrupt, basically what we've got to do is capture those. It's going to return those event link indexes that we need, and we're just going to attach event link interrupt. We need the code that we want, which interrupt. So this is the RD interrupt, and then which handler, a pointer to the handler we want. So the last step down here is to start the first measurement, and we wrote a function to do that. We haven't filled it in yet, but we're going to do that next. So let's go right here, start CTSU measure, and now we've got our whole initial CTSU setup function ready to go. So let's go up and do the 2 handlers and the start function. So let's start with the start CTSU measure function. We only need 2 lines for it. We have to set our measurement channel, and we've already seen what that needs to be. And we need to fire our software trigger signal, and that's just writing a 1 to the CR0 register. Next, let's run up here and fill in our WR handler. The first thing we need is to reset our interrupt in the interrupt link controller, and the event link interrupt library is going to handle that for us. To do that, we're going to call reset event link with our event link index that we got returned when we attached the interrupt. Next, we're going to set the measurement channel again. And finally, we're going to write to CTSU SO1 again to move us to status 3 like we talked about earlier. So we're just going to set it to the same value we already had in it. For the RD handler, we have to start with the same thing and reset our event link. And then we're going to read the results from the counter registers. We're going to read from the CTSU SC and the CTSU RC registers, and let's set a flag to let our loop know it's time to print it. We'll go declare these in just a second. We're also going to restart the measurement cycle by calling start CTSU measure again. And let's run up here real quick and pop in our variables that we need. Remember to make them volatile because they're going to be used in an interrupt handler. So that should be all we need to get it going. Let's build a setup in a loop so we can test it out. Let's start setup by enabling our serial and giving ourselves a little output to let us know we're going. And then we'll just call our initial CTSU setup function that we wrote. In loop, we're going to put an if statement to trigger on that new data flag that we're setting in the RD handler. We'll set the flag to false. We need to turn the interrupts off while we read from the registers just to make sure that we don't get another measurement in between reads. We'll set up a couple of copy variables to copy the registers or to copy the volatile counters into. Turn the interrupts back on and print the results. And then a serial print line here so our output looks nice. So let's plug in the board and upload the code. I'm using a 22 nanofarad capacitor this time. Someone told me that on the Renaissance development boards they use a 10 nanofarad capacitor, and I found that the smaller values for the capacitor seem to give smoother results. We get the code uploaded, and right away we see results. And if we touch, they jump up just like they're supposed to. That's great, but a real touch sensor should work without making actual physical contact. So I cut this little piece of paper as a stand-in for a membrane on a touch panel. When we touch, we see that we get values that jump up, but not nearly as high as they did when we were making actual physical contact. If I take a screenshot so we can see the results, when we're not touching, we seem to get a counter value somewhere in the low 9,000s. And then when we touch, it seems to be a little bit over 10,000. A few dips below, but mostly over 10,000. Maybe some averaging or smoothing could help. So that's the initial setup for the capacitive touch unit. There's still a lot of parameters left to tweak on and things left to play with. Maybe I'll do another video soon where we'll do some experiments with it and play with some of those other registers and maybe look at the different capacitor values. Let me know in the comments if there's anything in particular that you'd like to see me experiment with. Be sure to subscribe to the channel because I'm going to have a lot of cool Arduino hacks coming soon.